So now, example number 7, as you can see here, we have a circuit. That this circuit has a mix of sources. We have an independent source and a dependent source. And as we said before, if we want to solve uh, for the Thevenin equivalent circuit, for circuits that have dependent and independent sources, in this case, we cannot switch off the independent sources and find the impedance right at the output because we have this dependent source. And so in this case, what we can do is to find the V open circuit and then find the I short circuit, and basically the Z Thevenin would be the ratio of the V open circuit to the I short circuit. So this is one of the approaches. Okay, so let's start here. We need to find the V open circuit right here. Okay, so I will redraw the circuit in order to make it looking simpler. So on this circuit, the impedances are already calculated, so you don't need to do anything for the capacitor here. It's already given you in ohms. So we have the following. And notice that the V open circuit is this. So we have 120 minus J40 60, and this one is Vx, and this one is 10 Vx. Phasor is already given to you for the source. So we need to find the voltage open circuit. So how do we solve for this problem? Now, we can use nodal analysis if we put our ground here and we say that this one is V1. So let me do this exactly the same way we used to do nodal analysis. So this is gonna refresh your memory. So we have a node here, and I'm calling this one V1. And we have a second node here, right? That I am calling it V1. Now notice that V1 is also V open circuit. But just for simplicity, because, sorry, V2. But just for simplicity, because you've been dealing with assigning voltages for your circuit, I use the same notation, V1, V2, but V2 is indeed VOC, which is the potential difference between this node and the ground, which is the same as the V open circuit. Now you only need to do the nodal analysis that you used to do for a circuit. And here, if I am to write the nodal equations, which are basically the most important part in those types of a question, because as you noticed, I'm giving most of the 80% of the grade mostly on the formulation. So the equation that you write for the nodal equation is extremely important. So in order for me to write the nodal equation at V1, so if I say nodal equation at V1 will be V1 minus 120, right? Now this is 0, which means I can remove it because as you know that sine 0 is going to be 0 anyway, and you will end up with only a real number. So V1 minus 120 divided by 12 plus V1 minus 0 over 60. I'm just going to keep the V1. And then V1 minus V2 over minus J40 equals to 0. Now, how would you make sure that you did not miss anything? You look at the currents that you have written the nodal equation for. Look at the number of the I would say the connections between the other component. I have 1, 2, and 3. Only 3, and this is what we have done. Then this is equals to 0. So this equation is the first nodal equation. My second nodal equation, which is at V2, as V2 minus V1 over minus J40 plus V2 minus 10Vx. Notice that this node here with respect to the ground is indeed 10Vx. My V2 minus 10Vx divided by 120 equals to 0. Now in nodal analysis, notice that we don't write the nodal equations at the nodes that are connected to the source if the ground is connected to the other terminal, which means I did not write a nodal equation at this point, at this node, and I also did not write the nodal equation right at this node. Why? Because I don't know the current and those sources and those voltage sources, right? I don't. So this is not gonna help me. So those are the two nodal equations, and as you can see in this in those nodal equations, I have three variables. I have V1, I have V2, and I also have Vx, right? Which I picked up from this dependent source. So I need to look in the circuit and see where is that Vx that I can write it in terms of my standard nodal equations variables. So what are the standard variables in nodal analysis? Can somebody tell me? What are the variables that I use in nodal analysis? The voltages, exactly. The voltages of the nodes are my variable in nodal analysis. So I need to find a relationship between this Vx that I picked from the dependent source and those variables that I use in nodal analysis, which as you can see, V1 and V2. So just looking at that's exactly correct. So just looking at Vx and V1, I can easily see from here that indeed Vx equals to V1. So rewriting those two equations, taking those two equations with Vx equals to V1, mm-hmm. Yeah. Now rewriting those two equations after substituting Vx with V1, I would get the following. So if I am to call this one 1 and this one 2, then I can say here that V1 minus 120 divided by 12 plus, say here, I have 60, 40. So if I multiply by 120, what do I get? So let me multiply V1, sorry, question number 1 by 120. What do I get? I get 10 V1 minus 120 plus, if I multiply by 120, 60 is going to cancel, so I end up with 2V1. Then this one is plus J. When minus J, when it goes up, becomes plus J. I have a 3 plus J, 3 V1 minus V2. This equals to 0, right? So if you multiply by 120, 40, and 120 will be 3, and minus J goes up, becomes plus J3. So this is the equation, I will call it 3. And then if I want to continue, this is going to be 10 V1 minus 1200 plus 2 V1 plus J 3 V1 minus J 3 V2 equals to 0. So the real parts here, I have 10 V1, I have 2, right? So I have 12 V1, then I have plus J 3 V1 minus J 3 V2 equals to 1200, or take V1 outside, then I have 12 plus J3 V1 minus J3 V2 equals to 1200. So this is my first equation. We call this one 4. Now my second, from 2, I have now V2 minus V1. I can also multiply by 120. So from 2 times 120, what do we get? Again, the minus J, when it goes up, becomes J. So multiply by 120 divided by 43. So J3 V2 minus V1 plus V2 minus 10 Vx is V1, 120 would cancel. So this is my now second equation. So if I distribute the J3, so I have J3 V2 minus J3 V1 plus V2 minus 10 V1 equals to 0. So I have here V1 as real and this one V1 imaginary. So take the V1 outside. What do I get? I get minus 10 minus J3 V1 plus 1 plus J3 V2 equals to 0. Right? And this is my second equation. We call this one 5. Okay. Now those two equations, I need them. So those are the two equations that I need to solve simultaneously. So in this case, what I can do is here, I can say here that V1 equals to, let me take, if I take V1 to the other side, it becomes 10 plus J3 V1 equals to 1 plus J3 V2, right? Then V1 equals to 1 plus J3 divided by 10 plus J3 V2. So this is from 5. Now if I take this, let me call this one 6, and I say sub 6 and 4, what do I get? I get 12 plus J3 times 1 plus J3 over 10 plus J3, right? Minus J3 V2 equals 1200 V2. Now I need to simplify this. So the best thing to do is I can go to the from rectangular format to the polar format in order to simplify that. So here I have, let's see here, I can probably do the 12 times 12 times 1 J3 times J3. So here I can do this 12 minus 9, right? J3 times J3 is minus 9. Then I have 12 times J3 and J3 times 1. So in this case, let's see this one. Here, what do I have? 12 as plus 36J, J3 times 1 plus J3 divided by 10 plus J3. And all of them are V2 minus J3 V2 equals to 1200. So 12 minus 9 is a 3. So we have here 3 plus J 39 divided by 10 plus J 3 V2 minus J3 V2 equals to 1200. Now we can go to the polar. So here, if you do the one in the denominator, I will do the one in the numerator. That will save us some time here. So we have first the magnitude, which is the square root of 3 squared plus 39 squared is 39.1.1, and the angle, both of them are positive, so it will be in the first quadrant. Tan inverse of 39 divided by 3, which is 29.51 degrees. What about the one in the denominator? Could you do that? Which is the magnitude is square root of 10 squared plus 3 squared is 10.44, and the angle is also in the first quadrant. Tan inverse of 3 divided by 10, which is 16.7 degrees. V2 minus J3 V2 equals to 1200. Now this one would be 39 divided by 39.1 divided by 10.44 is 3.75 with an angle of 29.51 minus 16.7 is 12.81. V2 minus J3 V2 equals to 1200.
Sure.
Yes.
So would you say the voltage is in magnitude is the magnitude of the x and y components of its complex polar, like a
Right.
rectangular form?
Yes. So that's what I said. For the numerator is square root of 3 squared plus 39 squared. Okay. So now what I want to do is to go to the rectangular, because now I have here V2 with a polar, and this one is rectangular. So I have to, since I'm adding those two vectors, then I have to go to the rectangular. So here, in order to go to the rectangular, I have 3.75 cosine 12.81 plus J sine 12.81 V2 minus J3 V2 equals to 1200. Then now cosine 12.81 times 3.75 as 3.66 plus J, which is sine 12.81 times 3.75, which is 0.83. So both of them are V2, V2 minus J3, V2 equals to 1200. Then 3.66 V2. I have a 3 minus J 2.17 V2 equals to 1200. So what you need to do here is basically then V2 equals to 1200 divided by 3.66 minus J 2.17, right? Then again going to the polar, so I have a 1200 divided by 3.66 squared plus minus 2.17 squared tan inverse for minus 2.27 divided by 3.66. So V2 equals to square root 3.66 squared plus 2.17 squared 25 tan inverse. The imaginary is negative and the real is positive, right? So where are you expecting the angle to be, in which quadrant? Which quadrant? Hmm. Fourth. So we have here minus 30 30.66 degree, and V2 now is 1200 divided by 4.25, which is 282.35 with an angle of 30.66 degrees. So this is V2, which is the V open circuit, right? So V open circuit is 282.35, 30.66 degrees. Now the next circuit is the I short circuit. I understand that this the circuit is I mean the question is considered long. So let's copy this. Let's go here. Mm, okay. So now in the short circuit, I don't have VOC anymore, right? And I will be looking for the short circuit current because of the wire that I connected between A and B. I need to calculate this I short circuit. So let's see what's going to happen. So this is my original circuit after I connected. Now what's going to happen? Of course, now I don't have, let's remove those V2 and V1 and see what's going to happen. Now, in this case, and I'll continue the node here, you will see that A would be the same in potential as B will all be the same as 0 at the ground. So potential wise, because they're connected, this whole thing now becomes ground, right? And that's expected because of that short circuit that I put. The potential difference between A and B now is 0, right? But what's this going to do to me? Here, let's see. If I am to do nodal analysis, and I said that this one is V1. Now, this potential here is 0, right? So in this case, if I am to write the nodal equation, it will be V1 minus 120 divided by 12 plus V1 over 60 plus V1 over minus J40 equals to 0. So this is going to be now my nodal equation. So let me write the nodal equation here. So why am I doing this? I am doing this in order to calculate the voltage here, which basically, if I calculate the voltage here, which is the same as Vx here, I can now find the current in this branch, right? And eventually, this Vx, the voltage here, is 10 Vx, which is 10 W1, will also result into a current. And then we will write the KCL at node A, at A here, at this node here, in order to find the total current. So let's do this. So the first nodal equation, which is V1 minus 120 divided by 12 plus V1 over 60 plus V1 over minus J. And by the way, this V1 is different than the other V1. So if you want to avoid the confusion, you can still call this one V3 if you want, just to avoid the same notation. Because remember, what did we say about any physical changes that you do to your circuit is going to result into a complete new circuit. So to avoid the confusion for you, you can call this one V3 just to make sure that this voltage is different than the voltage that you found earlier in the first circuit for the open circuit. Because we put the wire right here at the output, the circuit has completely changed, right? So let's find V3. As you can see, it's one equation, one unknown. So we have here V3. If we multiply by, let's see here, if we multiply by 60, what's going to happen? So this is going to be 5 V3 minus 120 plus V3. Minus J will go up, becomes plus J. 60 V3 equals to 0. So I have 5 V3 minus, we have here minus 600 plus V3 plus J 60 V3 equals to 0. So 5 V3 plus 1, I have 6 V3 plus J 60 V3 equals to 600, right? So if I divide by 6, I have V3 plus J10 V3 equals to 100, and V3 is 100 divided by 1 plus J10, right? Then we can find V3 as 100 divided by, again, square root of 1 squared plus 10 squared, which is 10.05, and the angle is tan inverse of 10, which is 84.29. So V3 is 100 divided by 10.05 is 99, so 9.95 minus 84.29 degrees. This is V3. So I found V3 here. Now if I want to find this current, let me call this one I3. Then I3 is V3 divided by minus J 40. So I have I3 as 9.95 minus 84.29 degrees divided by. Now minus J40 is a rectangular format complex number. I can convert it to polar. Minus J is minus 90. So I have here 4T minus 90 degrees. Why? Because I know minus J is minus 90 degrees, right? As a complex number. So I3 is 0.249, 90 minus 84, because minus 90 when it goes up becomes positive 90, so I have 90 minus 84.29, so 5.71 degrees. So this is I3. Now what about this current? And let me call this one IX. This current is IX is indeed 10 Vx. Now remember Vx is V3, right? Which is, so here we also have Vx equals to V3. So I have Ix as 10 V3, right? Minus 0 over 120. So 10 V3 minus 0 over 120. Or Ix is 10 V3 over 120. Or Ix is V3 divided by 12, whereas V3, which is V3 divided by 12. So I will divide 9.95. Let me write that. 9.95 divided by 12 minus 84, 129 degrees. So Ix is 9.95 divided by 12, which is 0.83.
Sure.
Yes.
This is going back a while now, but we found the voltages V1 and V2 before the capacitor broke the circuit. Am I correct?
We found the voltage again.
V1 and V2 from the original circuit. Did we end up using those?
No, because now after we put the wire between A and B, we did a physical change to the circuit. So V1 and V2, the numbers, those readings are invalid now in my new circuit. As you can see, what was called V2 there now is zero because of that wire that I connected between A and B. Is that right?
So we just we calculated V1 V2 for the circuit as normal, and then
We
after
found
that we created a short circuit.
That's correct. So from the first circuit, we found the V open circuit.
Okay.
From from the
What did
second
you
circuit, we need to find the I short circuit.
what did you get for V1 and V2 from the original circuit?
I got the V open circuit.
Yeah, what were the values you got it for the open circuit?
282.35 with an angle of 30.66 degrees,
Okay.
which is now zero because of that short circuit thing. Right? Now here I need to find, so we have the same angle, as you can see. Okay. So this is Ix, right? So I found I3, I found Ix, and now I need to write the KCL at A. So let me write KCL at A. What do I get? I have I3 entering. I have Ix also entering. And I have I short circuit leaving, which means that I short circuit now is the summation of Ix and I3. So now I have I short circuit as I3 plus Ix, or I short circuit equals to, how much was I3? 0.249. This is I3, IX. Okay. I short circuit is the summation of those two. So now I have to go to the rectangular form. So I have I short circuit as 0.249 cosine 5.71 plus j sine 5.71 plus 0.83 cosine minus 84.29 plus j sine minus 84.29. So I short circuit as cosine 5.71 times 0.249 as 0.248 plus j sine 5.71 times 0.249 0.248 plus cosine 80 minus 85 minus 84.29 times 0.83 as 0.0826 sine minus 84.29 is going to give me minus, so you have to be careful here, minus j times 0.83, which is minus 0.826, right? Now you add the real with the real, the imaginary with the imaginary. I short circuit is now 0.826 plus 0.248 0.33 definitely is going to be negative because the second one is greater. So we have 0.826 minus 0.0248. So that's going to be 8.08, which means I short circuit and polar will be square root of 0.33 squared plus minus 0.8 squared point 8 6, 5. Then you have tan inverse of minus zero point 0.8 divided by 0.33 will be in the fourth quadrant, minus 67.58 degrees. So this is the short circuit. Now the Z Thevenin is VOC divided by ISC, and this is, if you recall, divided by 0.865 minus 67.58 degrees, and Z Thevenin is 282.35 divided by 0.865 is 326.42, 30.66 plus 67.58, and this is going to be 98.24 degrees. So this is the Z Thevenin, and equivalent Thevenin circuit would be in this case which is 326.42, 98.24 degrees, and this one is going to be V Thevenin as 282, which is the V open circuit, 35, 30.66 degrees. Okay, so this is the Thevenin's equivalent circuit for that circuit that we have seen at the frequency that was not given to us. Okay. Any question about how did we? So you can look at this question as basically a review of everything that we have done. We've covered the Thevenin's equivalency. We've covered the AC steady states, manipulations, and all the calculations. We've covered how to deal with the impedances for reactive components such as the capacitor. We did KCL. We did Ohm's law. Basically, in this question, we've gone through most of the circuit, nodal analysis, most of the laws, and most of the analyses that we have learned in this course. Any questions so far about how did we tackle, how did we solve for this example?
Sure. Will something like this be on the exam? Because it took me half the class just to get to B1 and B2. That
If,
hard?
yeah,
No.
yeah. If anything that I will bring, the time will be considered very carefully. We have a 2 hour final exam, I believe, right? Any other questions? No other questions? Okay. So in this case, we will end it here. If you would like to see me solving other questions in the coming lectures, our Thursday lecture is our last lecture, I believe, which is a makeup lecture from a cancelled class already earlier. So if you have any specific question that you would like me to solve for you, please email it to me. Otherwise, we're probably going to continue solving the remaining two examples that we have here. Okay? You can still email me. I still need to get back to some of you who sent me emails. Still, if you have any question, if you have any specific example that you would like to be solved, please email it to me. You do have a tutorial today as well. And in today's tutorial, your TA is going to be solving several AC steady state analysis. So I really encourage you to attend to today's tutorial. And if you have any question that you'd like me to solve, if you have any question about the material, I think the best way is email it to me so we can do it on Thursday. We do have an office hour on Friday. Probably I will update the office hours since the coming weeks we don't have lectures, so we can start having office hours more often, office hours. And I also encourage you to submit your evaluation, your course evaluation. Those data are important to us. So please do not forget to submit your course evaluation. And if you have any question that you would like to ask me, please feel free to ask now or email me. Any other questions before we conclude the session? You're welcome. Have a good day, and I'll see you on Thursday, same time, 11:30. Have a good day. Thank you. You're welcome.